So we know that if we have a basis E1 through En for our vector space, then any vector can be written in terms of that basis with some coefficients. Now, how do you find those coefficients? Well, you'll have to solve some linear system. But the great thing about having an inner product is that you don't have to solve that linear system. So if E1 to En is an orthonormal basis, then we have an immediate formula for decomposing a vector. And it's just this. And so the proof is, once again, a pretty straightforward one. So since we know that V looks like A1 E1 plus AN EN for some AKs, we just have to do the computation to figure out what those AKs should be. So we can take the inner product, say with EK, both sides of this equation. So on the one hand we have V against EK, and then on the right hand side we have A1 E1 plus da 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 against EK. And then by linearity, we can split the sum and pull the coefficients outside. And oops. And then by orthogonality, all of these are going to be 0 except for the one in here, which is AK, EK, EK. So that'll be the only one that survives. So this is by the fact that it's an orthonormal basis, and it's the orthogonality part. And then this one, by the fact that it's an orthonormal basis, the normal part says that this one is going to be equal to 1. So that tells you then from start to finish that AK is the projection of V onto the kth element of our orthonormal basis, and that justifies the formula. All right. So now we know that V looks like the sum k equals 1 to n AK EK. Whoops, let's replace that A with VEK EK. So we will see in the next section where we talk about like minimization and so forth, that if we take this sum and we stop it prematurely, so instead of going all the way to n, suppose we go just up to m, we'll see that this is the best approximation to V in the span of these vectors. So here, presumably, we're going to take m to be less than n. We'll also see that this is the projection of V to the span of E1 through EM. And so maybe a picture to go with that would be useful. So let's see, so if we've got there we go. Okay, so something like this. And let's see, so if we have point over here and we look at its best approximation in the green subspace, that's down here, and so we have projected down this way, and maybe there's a basis for the green subspace consisting of these vectors right here. And then so we've got these components of the purple one. There we go. And then we've got the component in the orthogonal direction along the blue vector right here. There we are. Okay, so what's all this about? So in this picture here, we've got E1 and E2. Oops, those should be green. So here's vector E1 and here's vector E2, and then this vertical one is vector E3. I guess this isn't really according to scale because they don't all look like unit vectors, but they are. They're unit vectors. Honest, you have to trust me. I wouldn't lie to you. So then here's V, and so V is actually equal to V E1 plus V E2 plus V E3, and this purple one down here is just the first two terms of it. And that the key point of what I was saying is that this purple one right here is the closest point in the span of E1, E2, namely the green plane, to the original red point V. We'll talk much more about this later.